Okay, so let's start. Today I'll be talking about longitudinal fields. This is a part of the plasmonics section where we will find out that at the resonance with omega p, which is the volume plasmon frequency, there we start to see longitudinal fields. So what is longitudinal field? Now we are all familiar with the transverse nature of electromagnetic radiation that seeds from the fact that your electric field, this is the form of the electric field that we write for an electromagnetic wave, where all the notations are probably familiar with you. Now in such a case, when we put in for planar waves, we put divergence E is 0. By planar waves we mean that it has parallel wave fronts extending to infinity. Okay, so if divergence E is equal to 0 and you substitute E in this form, then you land up with something like K dot E is equal to 0, which tells you that the electric field will be perpendicular to K vector. Okay, and similarly for the H field will also be perpendicular to the K vector, and that is the definition of your electric field of transverse fields. Okay, so but however there are situations where you can start getting longitudinal components in the field, and that of course, as you understand, will arise from the fact that wherever this divergence E becomes non-zero, those situations are when you start seeing longitudinal components. Let's just see two examples. So let us consider a linearly polarized light. Okay, linearly polarized light, beam of light. So when this light is incident, let's say it's a beam of light, I am drawing the two extremas of the beam, and we pass it through a lens and it gets focused to a point at this point. So if you look into the electric field, because it's linearly polarized everywhere, it is in the same direction, so it will be polarized in this. It's oscillating, of course, it's an electromagnetic field. So at a given instant, let's say the electric field is like this, and so if you draw the electric field in these two arms, this also looks like this. And these two electric fields can be broken up into the two components. One is the vertical one and the other the horizontal one. And if you look into it, you'll find that at the focus both the horizontal components cancel each other, and what you are left with is a vertical component, and this is nothing but the transverse field that we are always familiar with. Okay, so this is fine, this is what we have expected. Now consider a different type of polarized beam. For example, let's say you can actually generate a radially polarized beam. How does it look like? It looks like a ring of light where the electric field oscillates radially, something like this. You actually can do it with a certain geometry of antennas. Now if this electromagnetic field is radially polarized and you do the same experiment, you bring the beam in and focus it using a lens. Then if you see now the electric field, it will be in this opposite direction, and so if you draw the same figures and then again break it into the two different, sorry, this is wrong. The vertical and the horizontal components, what you find is at the focus, the blue is the one, the horizontal component survives while the vertical component cancels each other, and what this leads to is longitudinal field, where the electric field is in the direction of propagation of the beam. So this happens, and in many cases it will be a superposition of both. You can have a longitudinal component and you can also have a transverse component. Now how does this fit into our plasmonic discussion? So for that, let's go back to our wave equations. Wave equation. What, if you remember, it's the curl of curly, which arises when you substitute the H in the curl of relationship, and you get to this form where you have minus del square D del T square. Now D is nothing but, if you remember, our epsilon, which is the dielectric constant, and epsilon naught E, where please remember epsilon is the dielectric constant, a dimensionless quantity. Okay, so if that is the case, the left hand side actually can be written as k dot E minus k square E. This is the left hand side, and the right hand side becomes mu naught epsilon naught del square E del T square. And knowing the form of the electric field, we know the derivative of with respect to time gives you a minus I omega. So this one can again be written as epsilon minus I omega square E. Okay, we have done the partial derivative, and this mu naught epsilon naught can be written substituted by C naught, a C. So what we have left here is minus, that comes from the I square, epsilon omega square by C square. It's not a, sorry, it's not minus, it's plus C square E. This is what we have. Now again, going back, for the transverse field case, for transverse field, k dot E becomes 0. So the left hand side becomes minus k square E. Okay, so this relation and which results in actually that the E's cancel out and you get a k which is equal to, k square is equal to omega square by C square epsilon, which is something which we are familiar with, right? Now we go to the longitudinal case. Longitudinal case. So it's the extreme longitudinal case. The k is parallel to E. Okay. So let's say we can say k, vector k is k some n cap, and E is E n cap, some unit vector. Okay. So if we substitute it now again in this relation, what we have is left hand side is k square E n cap minus k square E n cap, which is 0. So if this is left hand side is 0, then we have epsilon omega square by C square is 0. Of course, E is equal to 0. So for any E values, and if it is valid for any omegas, and of course the field can't go to 0, so the only thing that can go to 0 is epsilon goes to 0. That is, the dielectric constant is 0. So from here we can infer that wherever, this is important now, wherever epsilon or the dielectric constant goes to 0, we have longitudinal fields. Okay, and what we will find in case of our plasmonics is that at omega equal to omega p, that is resonance with volume plasmons, we have epsilon goes to 0 for omega equal to omega p, and that will tell me that at resonance you have longitudinal fields. Okay, And this longitudinal field, how it will appear is, we will do another class on this. So if you have a material, I mean the conductor of course, and you have light electromagnetic field shining on it from the top, so your electric field is transverse initially, so it is in this direction. An oscillatory electric field, the electric field lies in the plane. However, when the frequency matches omega p, there is an electric field in the longitudinal direction, and what happens is the cloud of electrons that are present here, the cloud of electrons, they actually shift to one side, and you eventually have some ions, a layer of ions on top. So the plus charge is here and the negative charges at the bottom. So if you think of it, it is like a layer of plus charge, and a layer of minus charge, which is generated, and it keeps on oscillating of course, because it is an electromagnetic field. So there is some thickness to that. You can call it, let's say, d. So not d, maybe I'll use the same notation we used in class. So it's u and the thickness, and so the amount of charge that will be stored here, charge per unit area, that is sigma, that can be written as number of charges per unit volume into u into e. Yeah, so NEU will be the charge per unit area of these sheet charges that are developed due to the oscillation, where u is the displacement of the electron cloud because of the longitudinal field. Okay, so this is where we stop today, and we will continue again later. Okay, thank you.